Hello everyone, welcome to another video of our beloved channel, Mr. Civilization. We are happy to have you here, and in our channel, we learn the true secrets about humans and civilizations. Today, if I told you that you can unlock your genes to your full potential, would you believe it? You look in the mirror and you see yourself. You believe that you are in control. You believe you make your own choices, that your will shapes your destiny. But what if I told you that you're not the one pulling the strings? What if the real power lies far beyond your conscious awareness, within the very fabric of your being? What if I told you that hidden deep inside every one of your cells, there's a silent war being waged? A battle for survival that has played out for billions of years, long before you or I ever existed. And what if I told you that you are a battlefield? For generations, the secrets of our DNA have remained locked away, an impenetrable code. But now, new discoveries are emerging, revelations that will rewrite our understanding of life itself. We are on the cusp of something truly extraordinary, the potential to unlock our genes. This is not just about science. This is about you, about who you are, why you are the way you are, and the forces that drive you. Are you a free agent or a mere puppet dancing to the tune of your genes? The answer is far more complex and more unsettling than you might ever imagine. Prepare to have your world turned upside down. Prepare to have your DNA unmasked. Are we just puppets of our genes? Or is there something more to the story of life? In his groundbreaking work, The Selfish Gene, Richard Dawkins challenges us to look at evolution from a radical perspective, not from the point of view of the individual, but from the viewpoint of the gene itself. Prepare to have your understanding of life turned upside down as we delve into a world of ruthless competition, subtle strategies, and a surprising glimpse of hope. This book is not science fiction. It's science, but it reads like science fiction. It appeals to the imagination. We are survival machines, robot vehicles blindly programmed to preserve the selfish molecules known as genes. This is the core concept. Dawkins invites us to explore the biological roots of selfishness and altruism. It is a mystery story, and we are about to begin. Chapter 1. Why are people? The very question of why people exist is a profound one. For over 3 billion years, life existed without understanding its purpose, until Charles Darwin finally put together a coherent explanation. It is about evolution, the process by which life evolved. This book explores the biology of selfishness and altruism. Many have tried to explain human behavior, but have misunderstood how evolution works. The core mistake is assuming that evolution is for the good of the species or group. It isn't. It is for the good of the gene. Dawkins will show us how selfish genes shape individual behavior. Imagine a Chicago gangster, tough, quick, and able to attract loyal friends. Knowing the conditions he survived in allows you to infer something about his character. This is the same logic Dawkins uses. Our genes have survived, sometimes millions of years, in a competitive world. Therefore, we should expect genes to be selfish. This usually manifests in selfish individual behavior, but can also lead to instances of individual altruism. We need to define terms. Altruism is when one increases another's welfare at the expense of its own. Selfishness is the opposite. These definitions are behavioral, not subjective. We are only concerned with observable effects, not motives. Examples of seemingly selfish behavior are plentiful. Black-headed gulls eat the chicks of neighbors, praying mantis females eat their mates, and emperor penguins push each other into the water to check for seals. Refusing to share food or mates is another more ordinary example. On the other side, there are acts of apparent altruism. Worker bees sting to protect the hive and die in the process. Birds give alarm calls to warn of predators and put themselves at risk. The most common is parental care, with birds pretending to be injured to lure predators away from their nests. These are examples, not proof. To explain these, we must avoid the misconception that organisms evolve to do things for the good of the species or group. That sounds nice, but it's wrong. The group selection idea says that groups whose members are willing to sacrifice themselves are more likely to survive, leading to a world filled with self-sacrificing groups. But within those groups, selfish dissenters will do better. They are more likely to survive and reproduce, and after several generations, the altruistic group will be overrun. Selfish individuals will also migrate in and ruin the altruistic group. Group extinction is slow, individual competition is fast. Evolution is blind to the future. Group selection has a great intuitive appeal. We are trained to admire self-sacrifice, but there is a muddle over what the target of our altruism should be. Family, nation, race, species, all living things. And speciesism, giving preferential treatment to our own species, is no more logical than racism. But the group selection theory lacks a sound basis in evolutionary biology. What level then? Genes. The fundamental unit of selection is not the species, the group, or even the individual. It is the gene. Chapter 2, The Replicators. In the beginning was simplicity. The universe is populated by stable things. Stable things are groups of atoms that are permanent enough to deserve a name. Complex molecules like proteins, like hemoglobin, are also stable because their chains of molecules fold themselves into precise three-dimensional shapes. Before life on Earth, some rudimentary evolution of molecules occurred through physics and chemistry. Then, a remarkable molecule was formed by accident. We call it the replicator. It could make copies of itself. This was extremely unlikely, but over millions of years, even improbable events can happen. The replicator was a template. It attracted small building blocks that automatically arranged themselves in a sequence that mirrored the replicator itself. These chains split and formed new replicators. Copying isn't perfect, and errors happened. These errors were cumulative. It wasn't just one replicator now, but many slightly different ones, all descended from the same ancestor. Some varieties were more stable than others, either because they were long-lasting, rapidly replicated, or replicated accurately. The primeval soup became a battleground, and the replicators that survived were those with higher longevity, fecundity, and copying fidelity. This is essentially what we mean by natural selection. Should we call these molecules living? It's just a word. But they are the ancestors of life. They are our founding fathers. The soup was limited. Replicators competed for scarce resources, and those that were more effective increased in numbers. Some discovered how to break up rival molecules, using the building blocks for their own copies. Others discovered how to protect themselves with a wall of protein, which may have been how cells first arose. Replicators began to construct vehicles for survival. The first survival machines were protective coats. Over time, survival machines became more complex. The ancient replicators didn't die. They are still with us, swarming in colonies inside gigantic robots, communicating with it by indirect routes, manipulating it by remote control. They are in you and in me. They are now called genes, and we are their survival machines. Chapter 3, Immortal Coils. Survival machines include all animals, plants, bacteria, and viruses, incredibly diverse in their forms, but uniform in their fundamental chemistry. The replicators they carry are basically the same in all of us. DNA. DNA molecules are long chains of nucleotides, twisted together in a double helix. There are only 4 different kinds of nucleotides, A, T, C, and G. What differs is the order in which they are strung together. These sequences are the instructions for building a body. DNA lives inside our cells. Each cell in your body contains a complete copy of your DNA, like blueprints in every room of a building. These blueprints come in 46 volumes called chromosomes. The genes are strung out along these chromosomes. DNA does 2 things. First, it replicates, making copies of itself. Second, it indirectly supervises the making of proteins. Proteins are the fabric of the body, and they control all chemical processes inside the cells. Genes control the development of a body. Acquired characteristics are not inherited. A body is the gene's way of preserving themselves. Replicators are not conscious or purposeful. The process of natural selection is blind. The qualities of a successful gene are very complicated now that they live inside large organisms. A modern replicator is highly gregarious. It lives with thousands of others, interacting in ways that are difficult to disentangle. But a gene is also a discrete replicator that survives through many successive bodies. This occurs because of sex, which mixes and shuffles genes. A single individual body is temporary, but genes are potentially immortal. One gene can be regarded as a unit that survives through many successive individual bodies. Our bodies are like loose-leaf binders, holding volumes, chromosomes, containing pages, genes. We have 2 copies of each chromosome. Sometimes the 2 genes are identical, Other times they're different. These are called alleles. Alleles are rival genes for the same slot on a chromosome. Sometimes one allele prevails, making the other recessive. When sex cells are made, a special kind of division called meiosis occurs. During meiosis, chunks of the chromosomes get detached and swapped. Each sperm or egg, therefore, is unique. The word gene has been defined many ways. We're using a gene to mean a bit of chromosomal material that potentially lasts for enough generations to serve as a unit of natural selection. A gene is a replicator with high copying fidelity. The shorter a genetic unit is, the longer it's likely to live, and the less likely it is to be split by crossing over. We're defining it by its potential longevity, which in the case of genes means longevity in the form of copies. A cistron, which is a length of DNA coding for one protein chain, qualifies as a gene, but so also do larger units. Through inversions and other accidental rearrangements of the genetic material, larger groups of genes that cooperate well may have come together. A gene is a selfish unit, competing with its alleles for survival in the gene pool, which is a new sort of soup where it makes its living. All that has changed is that nowadays it makes its living by cooperating with successive groups of companions drawn from the gene pool in building one mortal survival machine after another. Genes are not destroyed by crossing over, they just change partners. The genes are immortal, we are their survival machines. What qualities make a good gene? One is selfishness. Another is the tendency to postpone the death of their survival machines, at least until after reproduction. Lethal genes tend to be removed from the gene pool unless they're late-acting. Senile decay may be due to accumulation of late-acting lethals. Why do we use sex? Sex seems an odd way of copying genes because you only pass half of your genes on to the next generation. Sex benefits the genes for sexual reproduction. It's not about being efficient for the individual. Surplus DNA? From the selfish gene's perspective, there is no paradox. The true purpose of DNA is to survive, and some DNA might just be a parasite along for the ride. It is whole individuals who live or die, and the immediate manifestation of natural selection is nearly always at the individual level. But the long-term consequences are manifested in the form of changing gene frequencies in the gene pool. Evolution is the process by which some genes become more numerous in the gene pool, and others become less numerous. Genes are not in direct control of day-to-day decisions. They are in charge of building the brains that make those decisions. Our next chapter looks at how. Chapter 4, the gene machine. Survival machines were once passive receptacles for genes, but over millions of years, they evolved the trick of rapid movement, the province of the animal kingdom. Animals became gene machines. Animals achieved their rapid movement with the evolution of muscles, which translate chemical energy into mechanical force. Muscles move levers, which are our bones. But the timing of muscle contractions is complex. Animals use a nervous system, a biological computer made up of neurons. Sensory nerves connect the brain to sense organs, and motor nerves connect the brain to the muscles. Brains take information from the outside world, analyze it, and store it as memory. One of the most striking properties of survival machine behavior is its purposiveness. Machines that behave with a goal use negative feedback. A device measures discrepancy and works harder to reduce that discrepancy. A guided missile is a more complex kind of purposive machine. It has an apparent purpose and can even appear to predict and anticipate its target, but there is no consciousness involved. Genes control survival machine behavior indirectly, not directly. They set up the survival machine beforehand. After that, the survival machine is on its own. Genes can't manipulate our puppet strings because of time lags, like the Andromedans who had to program a computer in advance to take decisions on Earth 200 light-years away. Genes predict the future by programming brains to make good bets, to take decisions that pay off on average. Survival is the currency, strictly gene survival, but often individual survival works as a good proxy. Learning is one way that genes cope with unpredictable situations. Here's a list of good things: sweet tastes, orgasms, smiling children, and here's a list of bad things: pain, nausea, empty stomachs, screaming children. If you do something followed by a bad thing, don't do it again, but repeat anything followed by a good thing. This helps deal with a changing environment. Brains can also simulate the future. Simulation is vicarious trial and error. If you have a decision to make, you imagine the consequences of each option. Survival machines with this capacity are a leap ahead. The evolution of simulation culminated in subjective consciousness. This is the most profound mystery facing modern biology. But consciousness is not necessary for the argument of the book. We can still speak of machines behaving as if they have a purpose without arguing about whether they are really conscious. Genes are the primary policymakers. Brains are the executives. Brains took over more and more of the policy decisions, using learning and simulation. The logical conclusion to this trend, not yet reached in any species, would be for the genes to give the survival machine a single overall policy instruction: do whatever you think best to keep us alive. Does this mean that we have no evidence of genes directly influencing behavior? No. Remember the hygienic bees. Some bee colonies have a behavior called hygienic behavior, where they remove the wax caps from cells of diseased grubs, drag out the grub, and throw them out of the hive. Genetic experiments show there are two separate genes that are needed for these actions, one for uncapping and one for throwing out. This shows a gene can influence complex behavior even without us knowing the details of the causal chain. Genes work with other genes and their environment to influence behavior, but for our purpose, a gene for altruism is simply any gene that makes its possessors behave altruistically more than its allele would. Survival machines go to great lengths to find food, avoid being eaten, find mates, and protect their children. They communicate to influence each other's behavior using song, tail wagging, grinning, and language. Communication is not always what it seems. Liars and deceivers abound. Birds sometimes give false alarm calls to frighten others away, then eat their food. Anglerfish lure prey with a wriggling bait on the end of a fishing rod. Bee orchids mimic female bees to induce them to copulate with their flowers. Females of one firefly species mimic the flashes of a different species to lure and eat their males. Whenever a system of communication evolves, there is a danger it will be exploited. We should expect lies, deceit, and selfish exploitation to arise whenever the interests of the genes of different individuals diverge. This will include individuals of the same species. It also makes one wonder if communication signals evolve for the mutual benefit of sender and receiver, or rather, if all animal communication contains an element of deception right from the start, because all interactions involve some conflict of interest. Our next chapter explores the nature of these conflicts. Chapter 5: Aggression, Stability, and the Selfish Machine. To a survival machine, another survival machine is just another part of its environment. But another survival machine hits back, because it too is a gene vehicle. Natural selection favors genes that make the best use of other survival machines, and that can mean competing over food and mates. It might seem that the logical policy for a survival machine would be to murder its rivals, but murder and cannibalism are not as common as the selfish gene theory might predict. Konrad Lorenz described animal fights as formal tournaments with restrained violence. Whether a naturalist stresses violence or restraint depends on what sort of animal he is used to watching and his evolutionary preconceptions. Why don't animals always go all out to kill their rivals? There are costs to outright pugnacity. For example, if I kill a rival, I may remove him as a threat to me, but if there are other rivals, I am probably benefiting them as well. Also, a rival might fight back. Winning is not guaranteed, and fighting uses up time and energy that could be used for other activities. The decision to fight should be preceded by a complex cost-benefit calculation. Not every fight is worth engaging in, and a small victory might not be worth the cost. Maynard Smith has used game theory to make these calculations. He developed the concept of an evolutionarily stable strategy, or ESS, which is a pre-programmed behavior strategy. An ESS is a strategy which, if most members of a population adopt it, can't be bettered by any other alternative strategy. The only strategy that persists is one that, once evolved, cannot be bettered. To show this, we'll introduce two hypothetical strategies in a population: hawks and doves. Hawks fight as hard as they can. Doves just posture until one gives up. Hawks always beat doves, and when two hawks meet, they usually seriously injure each other. Each will win about half the time and get injured in the rest. If the rewards are scored at plus 50 for a win, 0 for losing, -100 for serious injury, and -10 for wasting time, you can work out average payoffs. If a population consists solely of doves and an individual dove wins half its encounters and loses half, its average score is plus 15. But a single hawk that enters the population will win all his fights and get a plus 50 score. Therefore, hawk genes will spread. If the hawks become numerous, hawk against hawk encounters will become common. The average score for a hawk in a hawk-dominated population is -25. Therefore, dove genes will start to increase. So there is an oscillation. There is also a stable ratio of hawks to doves, 7/12 hawks to 5/12 doves. When this is reached, the average payoff for hawks is equal to the average payoff for doves, and selection will not favor one or the other. An ESS is stable, not because it is good, but because it is immune to treachery from within. It cannot be bettered by any individual. An ESS does not require that each individual always plays the same strategy. Rather, each individual can have a probability of playing a certain strategy at any one time. Other strategies are retaliator, plays like a dove but retaliates if attacked. Bully, behaves like a hawk but runs if they are retaliated against. And prober retaliator, retaliates like a retaliator but will sometimes test if others will fight back. It turns out that retaliator is the only evolutionarily stable strategy. There are wars of attrition when there are no dangerous fights, where the resource goes to whoever is willing to wait longer for it. An ESS here is each individual waits an unpredictable time, on average waiting an appropriate amount of time for the resource. Individuals cannot betray what they are about to do. They evolve a poker face. These contests are symmetric, where individuals are identical except for their strategies. There can be asymmetries, though. Individuals can vary in fighting ability, and individuals may differ in how much they have to gain from winning. Finally, an apparently irrelevant asymmetry, like who arrived at a location first, can give rise to an ESS. For instance, the rule, if you are the resident, attack, and if you are the intruder, retreat, could be an ESS. The resident wins, intruder retreats rule has an advantage over the intruder wins, resident retreats rule. The latter would favor individuals constantly moving around to try to be the intruder, thereby making their behavior pointless. Territorial defense may be simply an ESS resulting from the fact that the territory holder was there first. But how would an ESS be affected by past experience? Animals can have both a general and a specific memory of past fights. Crickets use general memory. When one has won a large number of fights, they become more hawkish. After a losing streak, they become more dovish. If these crickets are kept together, a dominance hierarchy will develop. Animals like hens and monkeys have a specific memory of past fights with specific individuals. The individual memory of the outcome of past fights makes a dominance hierarchy even more likely to develop. What about interspecies contests? The interactions between species are usually not direct. Lions and antelopes may be competing for meat, but the lion cannot get meat unless the antelope loses its life. The lion does not hunt lions because this is not an ESS for them. It is too dangerous. Antelopes run from lions because a stand-and-fight strategy would not be an ESS for them. The lion and antelope became successful through evolutionary divergence that accentuates the original asymmetry of the contest. The invention of the ESS is a great advance in evolutionary theory. It enables us to understand conflict of interest and how independent selfish entities can form a coherent whole. It helps us look beyond what looks like a cohesive social organization towards the selfish strategies that cause it. It shows the value of the game theory perspective. It allows us to look at individual genes and recognize that while they are independent, they can be selected for their mutual compatibility. Genes do not have to be on the same chromosome in order to collaborate. As long as they do well in the presence of each other, this is all that is required for selection to favor them. Selection favors genes that can work with their environment of other genes. Even if they are not linked to each other, genes that work together well will still be favored. This brings us back to our basic concept. The basic unit of selection is the gene. Chapter 6, Genesmanship. What is a selfish gene trying to do? It is trying to get more numerous in the gene pool by programming the bodies that it lives in to survive and reproduce. But it can also assist copies of itself in other bodies. This would appear as individual altruism, but it is really gene selfishness. For example, a gene for albinism could help copies of itself in other bodies. This might mean programming albinos to be altruistic towards other albinos. But the chances that this specific double effect, albinism plus a tendency to be nice to albinos, is controlled by a single gene is small. It is more likely that a gene would recognize a copy of itself because it's a close relative. Close relatives have a greater than average chance of sharing genes. Parents towards their young is the obvious example of this, but also true for other close relatives, brothers, sisters, nephews, nieces, etc. A gene that causes its body to save 10 close relatives is more likely to be preserved than a gene for saving, say, 5. It's important to understand degrees of relatedness. Brothers and sisters share approximately 50% of each other's genes, as do parents and children. Cousins share 1/8 of their genes. The index of relatedness expresses the odds of a gene being shared between two relatives. As a rule, to get the relatedness between two individuals, identify all their common ancestors. Then, for each common ancestor, find the generation distance between each individual and that ancestor. Then multiply 1/2 by itself once for each step of the generation distance. If they have more than one common ancestor, you have to add the equivalent figure from all the ancestors. This means that a gene for saving more than 2 siblings, more than 4 half-siblings, or more than 8 first cousins would be successful in the gene pool. Genes benefit if they manage to help copies of themselves. Identical twins share all genes, like clones. An armadillo born in a litter of quadruplets should, therefore, be expected to show strong altruism towards its siblings. Parental care is a special case of kin altruism. You're equally related to your baby brother and your own child. However, brotherly or sisterly care isn't as common as parental care. We've now defined a gene as a length of chromosomal material that potentially lasts for enough generations to be a unit of natural selection. How long is long enough? Long enough for selection to show its effects. Genes are at least partly responsible for their survival. Genes manipulate embryonic development, ensuring the body is skilled at surviving. In this light, at the gene level, altruism must be bad and selfishness must be good, by definition. Genes are competing directly with their alleles for survival in the gene pool. Genes have no foresight, they do not plan ahead. Genes are just there, some genes more than others. They have an effect on the embryonic development of the bodies in which they find themselves, such that those bodies are a little bit more likely to live and reproduce. Genes cooperate and interact with each other and with the environment in inextricably complex ways, making such phrases as gene for long legs or gene for altruistic behavior convenient figures of speech. There is no gene which single-handedly builds a leg. It is a multi-gene effort dependent on external environment. But a single gene can, other things being equal, make legs longer than they would be without its presence. This is analogous to nitrate on the growth of wheat. The genes in a body are in the same boat. A good gene can get into bad company and get dragged under by a lethal gene, but replicas of that good gene will live on in other bodies that lack the lethal gene. Genes are selected for their ability to cooperate with their environment of other genes. The gene pool is that environment. A gene that is compatible with most of the other genes in the gene pool will have an advantage. This is why an herbivore's body needs the flat grinding teeth of an herbivore, and a carnivore's body needs sharp meat-eating teeth. Genes that cooperate well together are more likely to be selected. The smaller the gene unit is, the less likely it is to be split by crossing over, and the more likely it is to be shared by other individuals. Therefore, selfishness is to be expected at the gene level. The gene is the basic unit of selfishness. Genes can be selected for their ability to postpone the onset of deleterious genes, which could help explain aging. Selection will favor genes that postpone the operation of other lethal genes. Senility may be due to accumulation of late-acting lethal and semi-lethal genes. The more we can mimic the properties of a young body in an old one, the longer we might expect that body to live. Why sex? What's the point? Sex shuffles our genes, making the small genetic unit or gene the nearest thing we have to an independent agent of evolution. Why do our chromosomes cross over? Why don't we live forever? Because of selection acting at the gene level. Sex makes it less puzzling that DNA can be surplus. The true purpose of DNA is to survive. The simplest way to explain the surplus DNA is to suppose it is a parasite, or at best a harmless but useless passenger, hitching a ride in the survival machines created by the other DNA. Chapter 7. Family Planning. In the previous chapter, we spoke of helping kin. Now it's time to talk about family planning, a subject that brings group selectionists and selfish gene theorists into conflict. Survival machines have to make decisions about two things: caring for existing individuals and bringing new individuals into the world. Caring and bearing often compete with each other. The group selectionist would say that animals have fewer babies to avoid overusing the group's resources. A selfish gene theorist believes that individuals regulate their birth rates because it benefits their own genes. When human populations grow, they accelerate at an exponential rate. Famines, plagues, and wars are the ultimate limits to population growth. Birth control is a necessary, though unnatural tool to prevent that. We want to avoid a society based on the gene's law of universal ruthless selfishness. Wild animal populations do not grow at the same astronomical rates. They reach a stable size or go through boom and bust cycles. They do not increase indefinitely. Wild animals rarely die of old age. Death is usually from starvation, disease, or predators. Wynne Edwards believed that animals practice altruistic birth control for the good of the group. However, there is no evidence to suggest that this is what is happening. Individuals do have a clutch size, but for reasons that are selfish rather than altruistic. The selfish gene theorist's view comes from David Lack. Animals have a certain clutch size, not for the good of the species, but because it is the optimum for that individual. Too many babies, they spread their resources too thinly, and all die. Too few, and they have fewer descendants than others. The optimum number depends on their available resources. The resources a parent can provide is limited. Modern humans have changed this because the state can step in and support offspring beyond what parents are able to provide. But welfare states are very unnatural, and just because humans might share a moral ideal, it does not mean nature works in that way. In fact, the opposite is probably closer to the truth. Territorial behavior and dominance hierarchies, then, are just ways that individuals compete with each other to maximize their reproduction. Wynne Edwards also proposed the concept of epideictic behavior. He claimed animals perform mass displays or gatherings to help each other to assess their population numbers. This allows the group to voluntarily reduce their birth rate to avoid overpopulation. But this too is more easily explained on the selfish gene theory. An individual is making a calculation about the optimum number of offspring to have in a given year. Since overcrowding is a good indication of a poor environment, a gene for having fewer children when there is overcrowding would have positive survival value. This prediction can be achieved without any deliberate altruistic sacrifice at all. A good egg layer is simply trying to predict the optimum clutch size for herself. A good prediction mechanism could be a sign of overcrowding. By the same logic, if animals gathered in crowds to estimate population, each individual would make a pretense of thinking the population was higher than it actually was to persuade rivals to have smaller families. This is a beau geste effect, a lie that benefits the liar. In conclusion, we might say that Wynne Edwards' idea may be right, but for the wrong reasons. Individual parents practice family planning, but in the selfish sense that they optimize their birth rates, not restrict them for public good. Chapter 8. Battle of the Generations. The selfish gene theory provides a powerful tool for examining conflict of interest. If a mother must decide how to divide her resources among her children, which strategy will promote gene survival? The word favorite implies no subjective feelings, and the word should implies no moral obligations. A mother is a machine programmed to maximize the propagation of genes. How might a mother show favoritism? By investing her resources unequally. Parental investment is any investment by the parent in an individual offspring that increases the offspring's chance of surviving at the cost of the parent's ability to invest in other offspring. The best measure of parental investment is not in food or energy, but units of decrease in life expectancy of other children, born or yet to be born. A mother has a certain amount of parental investment in her lifetime. How should she allocate it? She must invest in the optimal number of children, but also equally in those that are the most likely to succeed. This means that, other things being equal, she will prefer to save the life of an older child over that of a younger one, because more investment has already been made in the older child. On the other hand, an older child may be more capable of feeding himself, so she may be more inclined to give a morsel of food to the younger child because he is in more immediate need. Weaning is a good example of this. When it is time to wean, it benefits the mother to invest in future children, and it benefits the older child to keep receiving milk. This is a conflict. The menopause in human females could be a byproduct of accumulating late-acting lethal genes. This means that older females who are less efficient at having children would benefit their genes more by investing in grandchildren. If she did have a grandchild and a child at the same time, she would prefer to invest in the grandchild whose life expectancy is greater. This may even be why women reach the menopause, since as a consequence, selection will favor genes for post-reproductive life. However, all of these calculations are from the mother's point of view. Children may influence how much parents invest in them. Even if parents don't want to show favoritism, children grab favored treatment. Children are as related to their siblings as their mother is to them, but children are also related to themselves twice as much as they are to their siblings. Therefore, children will want more than their fair share of parental investment, but only up to a point. As they grow older, they will benefit more if the mother diverts investment to future children. This may cause conflicts over when weaning should take place. The child will want more milk than is ideal for the mother, while still below what would be bad for the child's siblings. As time goes on, this line moves gradually in the mother's favor. Therefore, a conflict will happen over things such as weaning. The mother will be biased towards what is good for her, and the child toward what is good for it. These conflicts represent a battle of the generations. Not a conscious battle, but one that is dictated by selfish genes. How far should these conflicts go? Should a baby chick pretend to be more hungry than it really is? If its siblings are at risk, how selfish should a child be? Should they take more than their share, even if it is at the expense of their brothers and sisters? They should, to a point. A child should try to grab an unfair share, but not too much. For instance, a runt, who might be very ill or weak, could benefit its genes more by allowing itself to die rather than trying to grab more food, because his more robust siblings would stand a greater chance of success. Another conflict that arises because of this tension is over clutch size. In Chapter 7, we saw that the optimal number of offspring was from the parent's point of view. But if a parent doesn't know what the ideal clutch size is, she might lay one extra egg than she expects to be ideal, then carefully feed her offspring in order of their size, letting the smallest die first. This is one explanation for runts. We must view the child as a selfish machine. It will use every trick available, from lies, deceit, exploitation, and blackmail, to win over its parents. Even the baby bird's scream may be part of this strategy. If you consider the gene's viewpoint, each sibling's genes have a 50% chance of being shared in the other sibling, but the genes inside the chick itself have a 100% chance of being in the individual. So a chick is going to try and get more than its fair share from its parents, but up to the point that the overall net loss for the offspring in the nest is no more than double the individual benefit it gets from hogging resources. It can be difficult to determine when this threshold has been reached. A child will lose no opportunity to cheat, but there is a limit. There must be a balance. In the tug of war between genes for selfish greed and genes for being realistic about the net gain, the parent is in a difficult position. While it must strive to be fair, it is difficult to detect when its offspring are deceiving it. It is often argued that all genes benefit from the survival of parents, as well as children. But this is misleading. Genes are selected on the basis of effects. Genes which make children grab more than their fair share may therefore be at odds with genes that control parents' behavior. Children that manipulate their parents and force them to invest too much in them may seem to be doing so from the point of view of their own selfish genes. What about Alexander's claim that in this battle, the parent must always win? The genes of the parent have a long-term stake in their offspring's survival, and therefore will override selfish manipulation from the young. But Alexander's argument is flawed because genes must use the opportunities available to them, and not all genes are in the body of the parent. Alexander also overplays the genetic asymmetry between parent and child. In reality, genes will manipulate in whatever form they find themselves, young or old. The offspring will always try to get the maximum share. The parent will always try to maintain an equilibrium. It is a constant and ruthless tug of war with no guaranteed winner. Chapter 9. Battle of the Sexes. If conflict can exist between parent and child, how much more severe will it be between mates who share only half of each other's genes and only indirectly through their offspring? Both father and mother are interested in the welfare of different halves of the same children. There may be some advantage in cooperation, but each partner is trying to exploit the other and to make the other one invest more in the children while they themselves try to invest less. Ideally, what an individual wants is to copulate with as many members of the opposite sex as possible, leaving the partner to bring up the children. That is often what males try to do. This view of sexual partnership as a relationship of mutual mistrust and mutual exploitation has been especially stressed by trivers. What is the fundamental difference between maleness and femaleness? The answer is that the sex cells or gametes of males are much smaller and more numerous than the gametes of females. Eggs are large and nutritious. Sperm are tiny, little more than a package of genetic information. This is the only consistent difference between males and females. In simple species without differentiated sexes, all gametes are about the same. These are isogametes, and any individual can mate with any other. Then, evolution began to favor larger gametes, which meant a better start for an embryo. Then a small investment, exploitative strategy of small, mobile gametes appeared, leading to the divergence of the sexes. Eggs evolved to be large and immobile, full of resources. Sperm evolved to be small and mobile, their only purpose to fuse with the eggs. Because of this fundamental asymmetry, the mother invests more in the offspring from the outset. She's more committed to the child than the father is. This sets the stage for exploitation. Males can potentially father an infinite number of children, while females are limited by the time it takes to make eggs and raise young. The traditional view is that males should outnumber females 100 to 1. After all, a single male can fertilize many eggs. But this is not what we see in nature. Actually, the numbers of males and females are generally equal. Fisher gave the explanation for this. Suppose a gene arose making mothers produce mostly daughters. Such a gene would spread. Then, sons would become rare. If you had sons, you would have an enormous genetic advantage. In time, genes for sons would spread. The population will therefore stabilize at a ratio where the payoff from having sons is equal to the payoff from having daughters, and that ratio usually turns out to be 1 to 1. Fisher's analysis was important because he was one of the first biologists to show the value of thinking at the gene level, a new way of thinking about evolutionary problems. The genes will always behave as if they are trying to maximize their own chances of survival. Genes for femaleness are just as selfish as genes for maleness. All are trying to maximize the number of their copies in the future. Genes in a male will behave differently than genes in a female due to the different circumstances in which they find themselves. This is why males tend to be promiscuous and why females tend to be more coy. Since genes are always trying to manipulate their vehicles to their own advantage, they will, in both males and females, favor doing whatever works best for themselves. Both sexes will try to get the other one to invest more in the children. Males have more to gain from promiscuity, females have more to lose from it. The differences between males and females is due to these different interests. Therefore, a female might want to play hard to get to see which male will stick around the longest. This is the domestic bliss strategy, a way to weed out those males who are not prepared to invest. Some animals, such as birds, will not copulate until the male has helped build a nest or provided some resources. This helps to ensure that he is faithful, not just looking for a fast encounter. However, females that play this strategy can be fooled. Males can pretend to be faithful. They might even make false promises in their courtship. This means that females who are able to see through the deceit will do better. Therefore, females will favor a longer courtship. By engaging in a long courtship, a female can make males commit, thus making it more expensive for them to desert later on. But such long courtships favor genes for faithfulness. When males have invested in courtship, they are less likely to abandon the female afterwards. If a male invests a large amount in courting a female, it would be a waste to desert her. Therefore, males are sometimes forced to become faithful simply because they have been maneuvered by female wiles to be faithful. They could still be unfaithful, but it will cost them more than a male who had to invest little in the first place. Therefore, the existence of both fidelity and infidelity is to be expected, and this is borne out by what is known to happen in nature. There are indeed numerous species that practice lifelong monogamy, but then, many species go all the way to a system in which the females rear the children alone and have many different mates. Another strategy is what we call the he-man strategy. A female resigns herself to having no help from the father of her children, so she goes all out to select for good genes. She does this by being very choosy. She mates with the best males, those that she can determine to be the best genes. She is looking for signs of fitness and the ability to survive. Maybe they have strong muscles, perhaps long legs, or long tails as evidence of ability to attract mates, and the males will then have the attributes her sons will need to mate successfully in future generations. This can cause an unstable situation, with each generation selecting for the quality that the previous generation selected for, so it continues even beyond the point that it makes sense for survival. This can cause outlandish traits that are only useful for attracting females. This theory is called sexual selection, and it leads to the exaggerated traits we see in animals, such as the long tails of the bird of paradise and peacocks, and the antlers of deer. But Zahavi says it's not that a long tail is beautiful, but that it shows they have good genes, and they have been able to survive with it, in spite of it being a handicap. A male with a long and cumbersome tail is demonstrating that he is a he-man. Females select males who demonstrate they are not deceiving the females, and that the features they possess actually have a negative cost that must be overcome, so are honest. But again, this explanation does not hold up completely. If the handicap is a genuine one, why does it not harm the offspring? Moreover, a female wants her sons to have the handicap, but not her daughters. For all of these reasons, Zahavi's theory has met with skepticism, but like his fox-fox argument, his logic is quite thought-provoking. The major non-arbitrary asymmetry is fighting ability. If size confers an advantage, the best strategy is to pick fights with smaller opponents and avoid larger ones. But when the size advantage is slight, another paradoxical strategy might evolve, of picking fights with larger opponents and running from smaller ones. This is because individuals that behave in this way tend not to be injured. What are the common differences that tend to manifest themselves in males and females? It's the males that tend to be brightly colored, and females who tend to be drab. Why are males the ones with gaudy colors? They are the ones who are competing for the attention of females. Females are less fussy because, unlike males, they are limited by the numbers of eggs that they can produce, so they have less of a need to compete. And they are doing the choosing. Females are generally more choosy than males. The reasons for this can be to avoid mating with other species, but more importantly, it's because females have a higher stake in the success of each individual reproduction. In general, males tend to be more promiscuous than females, since they can father a large number of children with very little investment. Females invest more in the children than males, and must protect that investment. Therefore, they are more choosy. It's interesting to note how modern Western humans have an anomaly in the matter of sexual advertisement. In most species, it's the males that are gaudy, while females are drab. In our society, however, it's the females that have the gaudy clothes, makeup, etc., while men are more drab. This may be an indication that females are the ones that are now more in demand and have to work harder to attract males. You scratch my back, I'll ride on yours. We've looked at family, mates, and aggression. Now we'll consider other forms of animal interactions, such as group living and apparent altruism. Animals live in groups for many reasons. They may gain protection from predators, be able to take larger prey, conserve heat, or use other members to gain a hydrodynamic advantage. When predators go after the closest prey individual, each individual will try to avoid being the nearest. In a group, the domain of danger will shrink as individuals gather together into a tighter and denser grouping. But animals also help each other by actively taking steps to preserve members of their group. When they do this, how can this be seen as selfish gene behavior? Take, for example, bird alarm calls. There is evidence to show that alarm calls help others, but also attract predators to the caller. Why then do they give the calls? One answer lies in kin selection. If the caller is saving close relatives who share the same gene that makes them call, it will be a benefit for the gene pool to call. Another, more selfish explanation has also been given. The cave theory suggests that the caller is warning others in the flock so that they do not accidentally draw the predator's attention to the group. A similar theory is that of the never break ranks idea, where individuals call so that other flock members will fly to safety as well. Breaking ranks might attract predators. Whatever the theory, alarm calls are designed to be discreet to avoid attracting a predator's attention. The Stodding-Thompson's gazelle seems different, though. It seems to deliberately attract the predator's attention by its conspicuous leaps. Zahavi suggests that the gazelle is actually advertising itself to the predator. Look how high I can jump. You can't catch me. Go after my neighbor. Therefore, this is not an example of altruism, but an attempt to look like a bad target for a predator. What about kamikaze bees? The workers are sterile and can't reproduce, so sacrificing their lives isn't much of a cost. Their actions benefit their genes because it benefits the colony. All their efforts are devoted to the preservation of their genes in the colony, not through their own offspring. Social insects form a superorganism. All work for the good of the colony, with information, food, and labor widely shared. The worker bees are just another part of the body, like a liver or a muscle. In social insects, many workers are sterile, others are reproductive. They come from the same mother. Is the queen having it her own way by manipulating the workers? Or are the workers farming their mother and manipulating the queen? It's not either or because, as Hamilton realized, the workers are more related to each other than to the queen. This is because ants, bees, and wasps have an odd system of sex determination. Males develop from unfertilized eggs and have only one set of chromosomes. Females develop from fertilized eggs and have a double set of chromosomes. Therefore, a son gets all his genes from his mother, and a daughter receives half from the mother and half from the father. Sisters inherit all of their father's genes as identical copies. Therefore, full sisters share 3/4 of each other's genes, while they only share 1/2 of their mother's genes. This explains the sterile worker and why they are willing to sacrifice themselves. A gene for vicariously making sisters replicates more rapidly than a gene for making their own offspring directly. This means they are more related to their sisters than they are to their own offspring. From the worker's point of view, they would prefer to have sisters over brothers. From the queen's point of view, all offspring are equal. This is a battle of the generations at a cellular level. Each are trying to maximize their own genes in different circumstances. Trivers and Hare have shown that, indeed, worker ants seem to bias investment in favor of females, but the queen is only able to have her own way in species of slave-making ants. The slave makers enslave other ant colonies and use the slaves to care for their brood, leaving the queen in a position to control what kind of brood gets made, using the slaves rather than her own daughters. The main point is that all these behaviors can be explained by gene selection. It is a gene pool that is being modified, not a group, a species, nor an individual. And it is selfishness that powers the system, but it may often lead to cooperation. The social insects also have other amazing capabilities, farming fungi, tending aphids. They have complex systems for sharing food. Bees are an example of a species that is able to share information about where food is found. The traditional view is that all of this is designed to foster mutual benefit. However, we must expect that such systems can also be exploited. Whenever communication systems evolve, they can also be used to deceive. When different species work together, we call this mutualism or symbiosis. And there are many examples of symbiosis between different species where the different parties seem to benefit equally. But what happens if there is a delay between the giving of the favor and its repayment? This opens up opportunities for cheating. The answer is reciprocal altruism. You scratch my back, I'll scratch yours. A bird may allow another bird to remove ticks from its head. The other bird may reciprocate later, but the other bird could also cheat. How do you prevent that? W.D. Hamilton and Axelrod analyzed this using the idea of a game called the prisoner's dilemma. This has been used in many fields, from economics to defense planning. The game works like this. There are two players who each have two cards labeled cooperate and defect. They each play one card face down without knowing what the other player chose, and a banker pays each accordingly. If both players cooperate, CC, the banker pays each player $300. If both players defect, DD, the banker fines each of them $10. If one defects while the other cooperates, DC, the defector gets $500, while the cooperator gets fined $100. If you switch roles, CD, then the payoffs are flipped. What is your logical move? If the other player plays cooperate, I get $500 by defecting, and if he defects, then I am better off also defecting to only get fined $10 rather than being exploited by cooperating and losing $100. So whatever the other person does, I should defect. But that logic applies to both players. If both players follow the logic, they will both defect and both lose out. If they could cooperate, both would win. It's a dilemma. But the game can also be iterated, meaning it's repeated an indefinite number of times. In this case, players can learn from each other and build trust, retaliate, or be forgiving. In such circumstances, strategies may evolve that encourage mutual benefit. Axelrod held a competition in which expert game theorists submitted strategies. The winning strategy, which was surprisingly simple, was called tit for tat. Tit for tat begins by cooperating, and after that, simply copies the other player's previous move. It is nice, never the first to defect. It is forgiving, punishes only once, then cooperates again. In an iterated prisoner's dilemma game, the important thing is that you do not know when the game will end. If the game had a specific number of turns, it wouldn't matter since, eventually, both players would defect on the last move. But when the shadow of the future is long, reciprocal altruism may thrive. Axelrod defines a nice strategy as one that is never the first to defect. In his tournament, he found that nice strategies were the most successful. Another quality was forgiving, which means having a short memory. Retaliation was useful, but forgiveness was also necessary to get out of runs of mutual recrimination. Finally, it is useful for a strategy to be not envious, where it is not trying to beat the other player, but simply trying to maximize the overall payoff. Axelrod's work showed us how selfish individuals can come to cooperate with each other. But to do so, they must have the ability to remember past actions and also to interact with the same individuals repeatedly. One player's choice of strategy needs to be contingent on the other player's prior moves. But what about the real world? How do these rules apply to real animals and plants? They are playing their own iterated prisoner's dilemma. Bacteria can turn nasty when their hosts are injured. Fish clean each other's mouths. Vampire bats share blood. All these can be explained by the principles of the iterated prisoner's dilemma. There is nothing mystical or fanciful about it. Reciprocal altruism played an important role in human evolution, shaping characteristics like guilt and gratitude, and fostering a desire to detect and avoid being cheated. The human brain is designed for ever more devious cheating and ever more subtle detection of cheats. Chapter 11. Memes, the New Replicators. Is there anything that is unique about humans? Yes, it's our capacity for culture. Culture is transmission of ideas through imitation. It is not unique to humans, but in our species it is a potent force. Culture evolves rapidly. Genetic evolution is slow in comparison. The laws of physics are universal. But are there universal laws of biology? Probably yes. All life evolves by the differential survival of replicating entities. The gene is one such entity, but there may be others. A new replicator has arisen. It's called the meme. A meme is a unit of cultural transmission, a unit of imitation, such as a tune, an idea, a catchphrase, a clothes fashion, a way of making pots, etc. Memes propagate themselves by leaping from brain to brain via imitation. If an idea is copied from brain to brain, it is a successful meme. Memes literally parasitize brains, turning them into vehicles for meme propagation, like a virus does to the genetic mechanisms of a host cell. Consider the idea of God. How did it arise? It replicates itself by the spoken and written word. Its survival value results from its psychological appeal. It provides answers, promises justice, and a cushion from inadequacy. That is why the idea of God is copied so easily. God exists as a meme in the meme pool. But why does the idea of God have a psychological appeal? Why should brains be receptive? We tend to explain biological phenomena in terms of gene advantage, so we must ask why a brain like ours is conducive to the meme of God. Our brains were built to favor gene survival. But evolution is not something that anyone wants or is seeking. It is something that happens. When new conditions allow it, new replicators will arise, creating new kinds of evolution, independent from their gene-based origins. Genes provided the soup in which memes arose. Once self-copying memes had arisen, their own evolution took off, and they became a force in their own right. We cannot limit our analysis of evolution simply to the gene. The meme pool can be seen as analogous to the gene pool. Memes compete with each other for brain space, radio and television time, and column inches in the newspaper. What qualities make a meme successful? Longevity, fecundity, and copying fidelity. Memes do not always replicate perfectly. They tend to be altered as they are passed along from brain to brain. This is similar to genes that undergo continuous mutation and blending. What exactly is a meme, or how many memes is a symphony? A single phrase of a symphony that is easily remembered and transmitted can be a meme. The important thing is that a meme is any entity capable of being transmitted from one brain to another. The specific form may not matter so much as the core concept that is held in common between the different versions of the meme. Genes are units of selfishness. What about memes? Do they behave as though they were self-interested? Yes, because brains, the computers that house the memes, are limited. There is competition between memes for limited space and time within the brain. Some memes form mutually assisting groups. Religious practices, traditions, and ceremonies can be regarded as meme complexes, such as the Christian Church, with its music, architecture, rituals, rules, and traditions. All serve to bolster belief in the central meme of God. Such meme complexes often include a blind faith meme, which discourages any skepticism towards its beliefs. Some memes and genes can reinforce each other, but sometimes they conflict. The meme for celibacy, for example, can be successful in the meme pool, even though a gene for celibacy is doomed to failure in the gene pool. But from the gene's viewpoint, we can see that genes can also be the victims of their carriers. By creating a world where memes can thrive, genes have provided the conditions for the creation of powerful ideas that may sometimes undermine their own success. It is the potential immortality of a meme in the form of copies that makes it a good candidate as an independent unit of evolution. Individuals are just fleeting, temporary structures that serve only as vehicles for the genes and for the memes they carry. We may hope to achieve something that no other animal has ever achieved, to defy the selfish genes and selfish memes. We are built as gene machines and cultured as meme machines. But because we have the capacity to think about the future, we have the power to defy the tyranny of the selfish replicators, both genes and memes. We may even begin to understand how we might cultivate pure, disinterested altruism. Chapter 12. Nice Guys Finish First. Nice guys finish last. A saying that embodies the idea that altruistic behavior is destined to fail and has often been used to define the basic assumptions of sociobiology. But what if it is only a half-truth? What if being nice under the right circumstances is a winning strategy? It turns out that when viewed properly, nice guys finish first. Remember the grudgers from Chapter 10. They are nice, except to those who have previously been nasty to them. Robert Axelrod, along with W.D. Hamilton, showed that this principle of reciprocal altruism has surprising power. He looked at a version of the prisoner's dilemma called the iterated prisoner's dilemma. This simple gambling game is deceptive in its complexity. It involves two players, a choice between cooperate or defect cards, and a banker who pays out or levies fines. The game is simple enough that it can be programmed into a computer. The game is played an indefinite number of times. Instead of a one-off scenario of betrayal, players must take into account the past moves of the other player. What strategy, then, will win? Axelrod held a competition, inviting experts in game theory to submit strategies to be played against one another on a computer. The winning strategy was one of the simplest, tit for tat. This strategy begins by cooperating, and after that, simply copies the previous move of the other player. It was both nice, it never defects first, and forgiving, a strategy similar to that of the Grudgers. After that, Axelrod conducted another similar tournament. Again, the most successful strategies were nice. It seems as though niceness pays. What makes this so successful? Axelrod's technical terms are key. Nice means to never be the first to defect. Forgiving means having a short memory. And not envious means striving to get more money from the banker rather than striving to do down the other player. To truly test the robustness of a strategy, you have to use the concept of an evolutionarily stable strategy, a strategy that does well when it is numerous in the population. A true ESS should never be able to be invaded by another. This prompted Axelrod to perform a third round of his experiment, where strategies were selected based on how well they did over a series of games. Only one type of strategy came to dominate, and it was a type of nice strategy like tit for tat. While not technically an ESS, tit-for-tat-like strategies are collectively stable, meaning that in practice they cannot be easily invaded. But this does not mean we can be totally nice. A strategy like always cooperate would be easily exploited by cheaters, and it must be protected with the threat of retaliation. In short, Axelrod showed that nice, forgiving strategies can outcompete the nasty ones if a population plays the game many times rather than just once. Nature is full of iterated prisoners' dilemmas. The cleaning fish we talked about in Chapter 10 engage in reciprocal altruism and are playing a version of the iterated prisoner's dilemma game with their client fish. Bacteria are playing this game in our bodies, choosing to cooperate or not with our immune systems. Vampire bats also seem to play it, choosing to share blood with those who had helped them in the past. We know that they recognize each other, and that it is those who are friends with each other that share their blood. A long shadow of the future is also important. If you don't know when the game is about to end, cooperation is more likely to evolve. A fascinating human example is what is called the live and let live system that arose during World War I. Troops facing each other in the trenches realized that mutual cooperation was a better option than continued hostility. They set up routines so that artillery barrages became predictable. They developed mutually understood rules of engagement. If they broke the rules, they risked retaliation from the other side. While from a political or nationalistic viewpoint, this cooperation was bad. From a survival point of view, for the individual soldiers involved, cooperation was a better option. Tit for tat and similar strategies that work well in the face of both nasty strategies and similar strategies that follow similar rules is not just about psychology, it is the key to understanding evolution. Another interesting example of a way that individuals can be drawn into a situation that is to their detriment is the one about lawyers in a divorce case. There is a good argument that, while many assume that a divorce is zero-sum, it should not necessarily be so. However, because of the adversarial legal process, it is set up as a zero-sum game, where the lawyers, working cooperatively against the interests of their clients, actually win. Spectator sports like football tend to be zero-sum games, but occasionally they can turn into a non-zero-sum game where both parties can win. This happened in English football, where two teams began cooperating with each other in order to secure a draw, and thus both secure a place in the top division. Axelrod's work teaches us that it is important that a system is a zero-sum or non-zero-sum game, and also that it is important how the players perceive the game. If one player assumes it is zero-sum, while the other player realizes it is not, those who fail to understand the underlying dynamics will lose out. Finally, if the world does turn out to be composed of mainly nice guys who are also capable of punishing nastiness, it is important to remember that they are only able to act that way because of long-lasting relationships with individuals that can recognize them and reciprocate. Chapter 13: The Long Reach of the Gene. There is an unease at the heart of the selfish gene theory. It's the tension between gene and individual, which is the fundamental agent of life. On one hand are independent genes skipping through generations, and on the other hand are integrated bodies with clear purpose. Darwinian selection does not act on genes directly, but via their effects on the world, their phenotype, usually on the body. But sometimes a gene has an effect that benefits itself but harms the body. This can be seen in meiotic drive, or segregation disorders, where genes bias the fairness of meiosis in their own favor. A mouse with a T gene passes that gene onto up to 95% of their sperm, even if it's a bad gene. These show that genes don't work for the benefit of the body or group, they only care about themselves. The individual, therefore, is just a byproduct. So if genes are selfish, why do individual organisms even exist? Why isn't the world still just a battleground of independent replicators? To get the answer, we have to rethink the idea of a phenotype. It must include all the effects a gene has on the world, not just those within the body in which it sits. We can call this the extended phenotype. An example is caddis fly larvae that build stone houses. A conventional geneticist would think of a gene for the caddis for building stone houses, but the house is not a part of the body. It is an extended phenotypic effect of the caddis genes. They are, therefore, genes for stone size or shape. If genes can influence objects like stones, they can also influence other bodies. Snail shells that are thicker as a result of a parasitic fluke are another example of an extended phenotype. It is the genes of the fluke, not the snail, that directly make the snail secrete an extra thick shell, and they don't necessarily do it to help the snail. This is because snails, if they had a say in the matter, may wish to economize on the amount of material used to make shells. Parasite genes reach outside their own body to influence phenotypes in other bodies. Fluke genes influence snail bodies, just as snail genes influence snail bodies. These fluke genes do not leave the host via the same route as the snail genes, and so there is a divergence of interest between them. The flukes want the snails to survive, but they don't care about their reproduction, so the fluke will make the snail make a thicker shell than the snail genes would have chosen to. And because it is not passing on its genes via the same method as the host genes, it has no need to worry about the fact that it is not also passing on a preference for thicker shells. A preference for a thicker shell will only make the host less efficient at reproduction. Therefore, the fluke is being selfish. This means we should ask about any parasite not what its effects are on the host, but rather if its genes are transmitted to future generations via the same channels as the host's genes. If they do, the parasite is more likely to help the host. If they do not, the parasite is more likely to harm the host. A prime example is ambrosia beetles, which have bacteria that live in their body and transmit their genes in the same way as the beetles, via the beetle eggs. The bacteria, then, are working to promote the survival of the beetle, since they will only survive if the beetle survives. In such cases, the bacteria may end up completely merging with the beetles, becoming almost like a single organism with shared genetic interests. The extended phenotype is about genes reaching outside the body. We don't have to just think of a fluke inside the snail or the caddis inside his shell. Cuckoos reach out via manipulation. A cuckoo doesn't harm its host directly, but exploits its parental instinct by having an irresistible red mouth to stimulate the host bird to give it food. A survival machine can only be thought of as being guided by its own genes indirectly, by the construction of a brain, or through chemical changes in the body. And those changes, those programs, can be extended out into the external world. The extended phenotype theory says we should ask whose genes are really benefiting from certain behaviors or characteristics. We should not blindly assume that it is the body doing those behaviors or possessing those traits. Beaver dams also demonstrate how far the long reach of genes can go. Beaver genes make the beavers build dams, but the effects of the genes go far beyond the beaver itself. The beaver dam is an adaptation of beaver genes, but it is part of the outside world. The beaver dam is the extended phenotype of beaver genes. What is the role of the vehicle in this? Is it always to be seen as a hapless victim or puppet? No. It just means that natural selection cannot favor a body acting to promote its own welfare. Instead, natural selection must favor genes that make a body act in such a way as to promote the gene's survival. If the gene finds itself inside a body, it must do its best to exploit that vehicle for its own purpose. Now, we can understand why bodies are separate and integrated. Bodies have an impartial exit channel into the future, that of the sperm and egg. This is not true of groups of animals, like a flock of birds or a school of fish, where the genes don't share a common destiny, or in a way that they do in a discrete single organism. The most fundamental reason why we don't find large, sprawling, cooperative organisms is that the genes inside do not share an impartial method of exiting to the next generation. It is that shared outlet which keeps the genes cooperating and pulling together. The body has been designed by natural selection to protect its genes during the organism's life cycle and to efficiently launch them into the future. It is that convergence of goals that gives each body its coherent purpose. What did our ancient replicators look like? They did not exist inside a neatly defined body. Replicators were scattered throughout their environment. They only came to form bodies when they needed to. The formation of bodies made them more efficient because they could cooperate more effectively to help each other. Cells arose to keep useful chemicals together and stop them from leaking away. Many celled bodies arose because size had its advantages. Cells became specialized for different functions. They cooperated even when those cells contained the same genes because it was in the shared interest of those genes to do so. So why do bodies participate in a bottlenecked life cycle? That is, why do they start as a single cell and grow? 3 reasons: back to the drawing board, orderly timing, and cellular uniformity. First, a bottlenecked life cycle makes it possible to evolve a new design without being limited by the old structure. New complex organs are only possible when we go back to the drawing board and start with a clean slate. It is not usually possible to remold an old structure into a new structure. So life must begin again from scratch each time. The bottleneck of the single cell provides a way to do that. Second, such a bottlenecked life cycle provides a calendar for embryology, where the growth phase is rigidly followed, such that genes can be switched on and off at specific points to regulate development. The precision of development requires that cells develop in a rigid sequence. This is because each cell has a specific location and time of appearance in the process. Third, bottlenecking has important genetic consequences. In bottle rack, each new daughter plant starts from a single cell, and all the cells in that plant are descended from it. Therefore, all are closely related. In splurgeweed, cells are more genetically diverse, and therefore more at odds with each other and more likely to be in competition with each other. Bottlenecking leads to uniformity, and when cells are genetically identical, they will be likely to cooperate together for the good of the individual and become what we call an organism. The selfish gene view of life applies to all replicators, everywhere in the universe. They are what make life possible and drive its evolution. Replicators, which are often DNA molecules, do what they must to get themselves copied. Over time, these replicators evolve to produce more and more complex methods of ensuring that their copies reach the next generation. They survive by virtue of their consequences on the world and by exploiting that environment to their own advantage. Those consequences can be indirect and can involve manipulation of others. These indirect effects will shape the world as we know it, from beaver dams to cuckoo nests, and from the color of a flower to the way a person writes a song. Genes that do these things prosper in the gene pool because these behaviors help them get to the next generation. Replicators gang up and create new types of vehicles. Ultimately, it is the replicator, whether it's a gene or a meme, that shapes the world as we know it. The selfish gene challenges us to reconsider everything we thought we knew about the nature of life. It shows us that evolution isn't about progress or morality, it's about the ruthless pursuit of self-replication, and it uses individual organisms as vehicles for its propagation. Yet, by understanding these underlying principles, we also become aware of our unique human capacity for consciousness, foresight, and perhaps true altruism. We alone can rebel against the tyranny of the selfish replicators. Thanks a lot for listening to this video, and don't forget to like, comment, and subscribe to our channel, Mr. Civilization, to learn the true secrets of humans and civilizations.